All right, so have you copy this down as I work through these problems, okay? So it says let f be function defined by x squared e to the negative x. No, just the function.
Okay.
Okay, it says find each relative max, relative min. So we're going to have to go through f prime. Okay. Create a sign line. Okay, so to get f prime, can you tell what rule is required here? Product rule, yeah. And also we have a special rule for e to the x, or e to the u is e to the u times u prime. Okay, so product rule. Okay, f prime times g. F. Okay, what's g prime going to be?
I said e to the time.
Yeah. Okay, do a little bit of cleanup. I can pull this negative out in front here. Okay, we want to create a derivative sign line, so we can take out a GCF, set equal to 0. What do you think our GCF is? Okay, that's part of it. Anything else we can take out? Yeah, you can take an x out as well. Okay. And so we're left with 2. All right. Take the x and e to the negative x out. We're left with 2 minus what? X. Okay. All right. Set f prime equal to 0. So x equal to 0, e to the negative x equal to 0, 2 minus x equal to 0. Okay. You try to set e to the negative x equal to 0, well, we won't get anything in return. This is undefined. So nothing here. Just x equals 2 and x equals 0. Okay. We create our f prime derivative sign line. Test values in each subinterval. Right. Okay. Well, we can maybe think of it as a different way here. Maybe you want to think of it as f prime as x times 2 minus x over e to the x. Makes it a little bit easier to work with. Push that e to the negative x down to the denominator. Okay, so now we're going to test each value. So -3 goes in for x. We get negative times negative, which is positive, over e to the -3. Now, e raised to any number, doesn't matter what it is, it's always going to be positive. Okay? Because e to the x graph looks like this. All right, doesn't matter if you plug in -1, -2, -3, 5, 6, they're all positive y values. Right? So you got positive over positive, so it's positive. Two minus x. Okay. Plug a -1 in. -1, that's positive. Sorry, negative. 2 minus -1, that's positive. Negative times positive is negative. We know the denominator is always positive. Okay, we enter 1. 1 times 2 minus 1. Positive over positive is positive. Okay, does everything make sense here? Okay, so what do you expect the -2?
Oh wait, max.
Max, right? You see the graph is rising and then falling, so there's relative max, and here relative min because it's falling and then followed by rising. Okay. Okay, so how can I find the physical locations of these ordered pairs? Original, good. All right, so original. Now, this is e to the negative x, so if I raise e to the -2, then that becomes e to the +2, right? So I have -4e squared. So let's say f of -2 means I'm going to insert -2 into the x.
Yeah.
So it's +2, right? So this is really 4e squared. Yeah, so there's my y value. Relative min, 0 into the original function. Anything times 0 is just 0. Okay, good. All right, here's number 2. This is a particle motion problem. Position. So part A says find velocity function. Okay, so take a look at how this is set up. What method is involved here if we want to find the derivative to get from position to velocity?
Chain?
Not chain. Now, we would need chain if there's a parentheses with a messy exponent, like parentheses raised to the 5th power or something. Product rule, okay. Which part would require the product rule? Yeah. That's your one function. That's a second. That's just a constant, right? That constant was a standalone. We know that's going to go to 0. It's this is going to be what will have some effect. Yeah, chain rule is a function within a function. I guess there's a little bit of a chain rule here, but usually we think of chain rule as parentheses, messy term outside, messy terms inside, messy terms outside, messy exponent outside. Okay. Okay, remember that the derivative for e to the u is e to the u times u prime. Okay, what's f prime going to be? G function, back to f. And what's G prime? Let's do some cleanup, and then for part B, we can find the acceleration, which is another derivative down. Do you see an easy GCF that we can take out to make it a little cleaner?
The two.
Yeah. Okay. Yeah. Maybe we do that. Yeah. Maybe I'll distribute through first. Maybe easier to see it, but I think you're right. 12 e to the 3t 6t. Oh, these are like terms, so I can combine some like terms here. 12 minus 2 is 10. Take out a 2, e to the 3t. Right. GCF is 2 and e to the 3t. Good so far? Okay. For acceleration, f prime g plus f g prime. We go through, yeah, product rule again. F prime Okay, part C, when is particle moving to the right? We have to create a velocity sign line and then test each subinterval. So we set velocity equal to 0. Nothing will come out of this. We know that exponential function e to the x is just always going to hover above 0, so it's never going to be equal to 0. So none here. Here. T equals 5/3. Velocity sign line. Okay, test each subinterval. Here I can choose 1. Here I can choose 2 or 3. 5/3 is more than 1, but less than 2. Okay, plug 1 into the velocity function. 2 times e to the 3, that's positive. 5 minus 3, that's positive. Positive, positive, positive. Plug 3 in. 2 times e to the 9, that's positive. 5 minus 9 is negative. So moving right is going to be where positive velocity occurs. Now, beginning of this problem, it says that this position is for all real numbers. So this is going to stretch to negative infinity on this side. Okay, the reason it's moving right is because velocity is positive. Velocity is greater than 0. Okay, t equals 0 is the velocity increasing or decreasing. You guys remember, what do we look at to determine whether velocity is increasing or decreasing? Just acceleration. Yeah, this says if speed is increasing or decreasing, we look at both velocity and acceleration. Right? But velocity increasing, I know that the temptation is you want to look at velocity, but the word increasing is changing it. It's kind of asking for the rate of change of velocity, which is just acceleration. Okay, so we're just going to look at acceleration. Okay, so we're going to find a of 0. Okay, plug 0 into t. We don't really care about the value. We just want to know whether it's positive or negative. Okay, 24 e to the 0. That's 24 minus 0. That's going to be positive. So because acceleration is positive, velocity must be increasing. Okay, good. All right, number 3. Find dy dx. Okay, this looks like a mess, but pretend like this is an easier problem. Pretend like this was y is equal to natural log of 5 minus 3x over 2 plus 5x. Right? Is there anything that we can do with this problem to make it easier to work with? Do you guys remember this property here? Natural log of a over b can be expanded into what?
Natural log of a minus natural.
So this is just a more complicated version of it. This is log base 3, but it's still, it's still a log problem. So if I have log base 3 of a over b, I can still expand that the same way. Log base 3 of a minus log base 3 of b. Okay. We want to expand first because we don't want this to be one large problem. We would prefer this to be two smaller problems. Okay. So this is my a, this is my b value. I'm just going to expand it like the way I see it here. Okay, we can rewrite this. This is fifth root can be rewritten as what? To the power of what?
Oh, is it low?
Yeah, what's fifth root? Or how about the third root of x? How would you rewrite third root of x? Yeah, so fifth root of x, or fifth root of parentheses would be 1/5, right? Okay, we want to continue expanding. This term is ready, but anything else that we can do to make this easier to work with?
Oh.
Well, yeah, we could do chain rule, but we would prefer to avoid chain rule, because anytime we have a log expression, we have an easier time if we can do a lot of things with it to clean up. So remember this property here. If I have natural log of a to the n, power property, I can always bring the exponent in front, right? Without changing the overall value. So why not just bring it down, though we can just avoid chain rule. So we're still in our cleanup stage here. Okay, so now it's nice and clean for us to apply the derivative. Okay. You guys remember the rule for natural log of u? It's u prime over u. Remember that for natural log derivative? Okay. This is not log base e, this is log base 3. So it's going to look a lot like natural log of u, still that u prime over u, but then there's a little bit of conversion that needs to happen because it's base a and not base e. And base a just represents any base other than e. So it could be 2, it could be 3, it could be 5. They all kind of follow the same rule, same pattern. So the rule is 1 over natural log of a as a bit of a conversion. And then it looks a lot like natural log of u. It's just u prime over u. So in this case, our base is 3, so we'll just apply the rule for base 3. Okay, so log base 3, what needs to come first? Okay, and now it's going to feel like your natural log rule. U prime over u. What's u prime? Over. Yeah. Okay. 1/5 is the coefficient. That's just going to stay. Log base 3. Well, 1 minus, what's the 3x squared? It's part of it. I think it's 6x.
Okay.
Right? Yeah, so we bring the 2 down, then we subtract 1 from the exponent. There's still a 1 sitting here. Okay. Over x minus 3x. Yeah, that's basically it. I mean, we can do a little bit of cleanup, but okay, number 4. It says find dy dx. Here's our equation. Can you list out, there's 3 things that we need to involve here if we want to find the derivative. Can you spot them? What's needed here? Any ideas? So what can we do with this natural log of x root y?
Here's Y to
We can raise this to the 1 over 1/2. Yeah, over 1/2. And then what can we do? Product property, right? We can expand, right? So there's a log expansion going on here, right? Natural log of AB can be expanded to natural log of A plus natural log of B. What else? Bunch of y's here, so there's implicit going on. And there's something going on the right side. Anything stand out about the right side? Mm-hmm.
the X.
The x and the y cubed, right? It doesn't. You don't see parentheses, but these are 2 separate terms. They're being multiplied. So this product derivative rule as well. Okay, so log expansion. That's my a and that's my b. I'm just going to clean this up before the derivative starts. And we said that this is the same thing as natural log of x y to the 1/2, right? Taking that square root of y and bringing it up. So natural log of x plus natural log of y to the 1/2. Continue expanding. We can bring that 1/2 down. Okay. What's the rule for natural log of x? Now we're ready for the derivative.
We had to get to the LNS.
Oh, right. So we have a log expansion that looks like this. If I have natural log of AB, I can expand it into natural log of A plus natural log of B. Right? Just expanding here. And I can also push that exponent down in front as well. So do you guys remember the rule for natural log of U? Mm-hmm. Okay, so what does natural log of x turn into? Okay, derivative of 1/2 natural log of y. Yes, yeah, that's right. We can basically you're right. 1/2 times 1 over y, but then we're asking for y's derivative. So what needs to happen here? Yeah, we need to multiply by dy dx. Okay, right side. Product rule. f prime g plus f g prime. Okay, what's g prime going to be?
Square times.
Mm-hmm. Plus and minus. What does 3y turn into? So we're done with product rule for the xy cube.
Did you still use the dy or the dx?
Yeah, we still need that dy dx. Equals plus
Oh, 0.
0. Okay. All right, we have all these terms now, but we're done with the calculus. This is the hardest part, was to get to the calculus. The rest is just rearranging and trying to get that dy dx by itself. Okay, so move this x over to the right side, and I'm going to factor the dy dx out. So I'm going to skip a few. I'm going to just combine a few steps together here. You guys see that? I just moved that 1 over x over to the right, and I factored the dy dx out. Okay. Divide the parentheses over, and I have my derivative. Okay, guys, good? Okay, so this is number, I'm skip number 6 here, and I'll come back to 5. Okay, we can rewrite this. How would you rewrite this? Parentheses raised to what power? Part of, well, 3 over x, right? Okay. Now we need to recognize this as a variable expression raised to a variable expression, and we don't have a rule for this, okay? We don't. So we have to have a workaround. The workaround is log expansion, okay? If we can introduce logs to the problem, we can bring that down and we have much easier time with available rules. So this is log differentiation. This is where we introduce logs into the problem because we want to use those properties, because otherwise we would be stuck not really having anything else to do, because we are limited with the rules that we can use. So we take the natural log of both sides. I'm going to rewrite this to get it ready for my next step. I'm going to rewrite this as 3x to the negative 1. It means the same thing, it's just easier with my next step, okay? What can we do? Log expansion.
Can you bring the 3x?
Yeah, bring that down in front. Right. So we haven't changed anything, but we have made things easier for our next step. Okay, left side, this is derivative is implicit, but the right side is product rule. Okay, natural log of y becomes 1 over y dy dx. Okay, f prime g plus fg prime. Now we go through power rule and u prime over u for natural log. G prime, u prime over u. Okay. Multiply the y over to the right side. Do a little bit of cleanup. And what can we replace y with at the last step here? The original, yeah. Okay. Okay, so the -7 goes in for the y.
Good morning.
And we have to understand that this is the x value that's showing, but it's really the y value of the original. I'm just going to bring that 7 over to the right side. And now it's a little bit of a guess and check, trying to figure out, okay, what x value will cause this to be true? And if we go through guess and check, our x value is going to be -1. Okay, there's a little bit of chart that we go through here. We know that this is the x value that we're really going to be working with. So all we do is we find the derivative at this x value, find the slope, and whatever the slope is, we can just flip it around to get the slope of the inverse. Okay, so derivative, sorry. F prime of x is just 3x squared minus 6x plus 5. Find the derivative at -1. So 3 plus 6 plus 5 is 14. The slope is 14, which means that the reciprocal must be 1 over 14. So we kind of played around with those problems in the last unit.